Hello, and welcome to 123 AP Physics 1 with Zach Speaks the Science Geek. Last week we discussed vectors as a foundation for our study of physics, and now we will begin with our study of motion. There are only four major quantities in kinematics. There is time, which is measured in seconds and usually represented by a t, displacement, which is not the same thing as distance, and I'll be explaining that in the next slide. It's usually represented as an x or a y, or you might sometimes see it as a d. It's the shortest line between the beginning and ending points, which is why it's different than distance, and it's measured in meters. You have velocity, which is displacement per unit time, usually measured in meters per second. An acceleration, represented by an a, which is the change in velocity per unit time, and it's meters per second squared. So displacement versus distance. Displacement is the shortest line between 2 points, whereas distance is the total amount traveled. So if a car moves 50 meters and then comes back to where it was, there's no displacement, but the car moved 100. The distance was 100 meters. So just have to remember to keep that straight. Usually they'll be the same thing in most problems though. So that's most. Velocity. Velocity is actually two parts. There's beginning velocity and ending velocity. Beginning is represented as v initial, vi, or v naught, and ending as v or v final. So here's the major formulas you're going to need to know. V equals v naught plus at. So that means the ending velocity is equal to the initial velocity plus the acceleration times the time. V squared equals v naught squared plus 2ax. That's the ending velocity squared plus equals the beginning velocity squared plus 2 times the acceleration times the displacement. V plus v naught over 2 times by time equals displacement. So this is basically saying the average velocity times the time is equal to the displacement. The displacement is equal to v naught times by t plus 1/2 at squared. And the displacement is equal to v times by time minus 1/2 at squared. Those are your 5 major formulas that you'll need to know. Okay, so far these 5 formulas, they all apply in one dimension. But what if it was 2-dimensional? What if the motion and what if you had gravity, which points straight down, but a ball was launched at 45 degrees straight upwards? There's an x and y component. Well, this comes to one of the fundamental concepts for kinematics. Motion in the x and y directions are independent of each other. Therefore, acceleration due to gravity would be only in the y direction. The only thing common between the two dimensions is time. So what you would do to solve a problem like that is you decompose the initial velocity and sometimes the acceleration into vectors, and then apply the formulas, and then at the end you might have to reunify it. So you just treat it as a bunch of vectors and then use these formulas. So this is a little handy shortcut. If a curve, a parabolic curve or a projectile motion problem, if there's no displacement in the y direction, then the y velocity vector is going to be equal in magnitude and opposite in direction of the original. And so that means usually that you just flip the vector around. The x would stay the same because usually there's no forces acting on the x direction. So just a handy shortcut. Okay, so we're going to talk about graphs for a few minutes. There's 3 operations you can do with graphs. You can find the slope, which gives units of y over x. So, like, the slope of this line. And if this is position versus time, then the slope would be position over time, which would be velocity. So it gives you units of y over x. You could read the axis and determine x as a relation of y. So like at 10 seconds, what is the position? And it'd be, you just look at 10 and you go up to the line and read the y-axis. And you can find area under the curve, which gives you units of y times x. So if you were finding the area under curve of this velocity, if you found it at this time, it'd give you the position, because velocity times by time is position. So it'd be that. And in AP Physics, they're usually going to not require integration. Once you get up to Physics C, it would require integration, but in just AP Physics 1, it's just usual easy geometric figures like triangles and stuff. So, oh, and an important note about the area under the curve is that the shape is under the x-axis. So if this line was down here instead, then the area under the curve would be negative. So that means like if the velocity was negative, it'd be going, the position would be going negative in the negative direction. So you just have to remember that, because sometimes you'll have a problem where it like starts here and then it goes up for a while and then it goes below the x-axis, and you have to remember that this subtracts from this. So the area under the x-axis subtracts from the area above the x-axis. So okay, so in kinematics there's three major graphs. You can see them over here. Thanks for I just googled kinematics graphs, and this was a good one I found. It's from a SlideShare user named CPP Physics. So just wanted to know that I'm not stealing his stuff. I am citing him. So in kinematics there's three major graphs. There's position versus time, where the slope is velocity, and if it's quadratic, like this one right here, the object is accelerating. There's velocity versus time, where the slope is acceleration, and the area under the curve, AUC, is change in position, as I was saying. And then acceleration versus time, where the AUC is the change in velocity. So like that'd be the change in velocity. Okay, so here's our first problem. A car moves 50 meters to the west, then 100 meters to the east. What was the distance traveled, and what is the displacement? So you might be thinking, oh, if they're both 150 meters, this one's easy. Well, this, as I was saying, there's a difference between the two. The distance is 150 meters because you just add the two. But the displacement, you move 50 meters west and 100 meters to the east. So the displacement tells you it's 50 meters to the east. So, important difference, but usually in most physics problems, they're going to be the same because you're not going to be fluctuating back and forth. Okay, problem number 2. A car travels 100 meters in 25 seconds. What is the velocity? What would the velocity be if the displacement and time both double? So what you do is you just do displacement over time, so 100 over 25, and that gives you 4 meters per second. And then if the velocity, what would the velocity be if the displacement and time both double? You do 200 over 50, which is still just 4 meters per second. And that makes sense when you think about it. Physically, it makes sense. So problem number 3. A car initially traveling at 50 meters per second begins to decelerate at a rate of 5 meters per second squared until it comes to rest. What was the total distance traveled while it was decelerating, and how long did it take? Okay, so we'd go back to our physical relationships, and we'd say, okay, which one of these would give us what we need? So we'll go back, and the one that would give us what we need is v squared equals v naught squared plus 2ax, because we have the final velocity because it comes to rest, so that's 0. We have the initial velocity we have the acceleration, but we want to find the displacement. So it's just solving a linear equation, and an equation with one variable, and so we plug in values and say v naught squared over 2 times the acceleration is equal to the displacement, and so 50 meters per second squared over 2 times 5 meters per second squared equals x, so it'd be 250 over 2,500 over 10 is equal to x, so then x equals 250 meters. So, okay. And then how long did it take? So, we know final velocity, we know initial velocity, we know acceleration, we don't know time, so we'd use v equals v naught plus at. V naught over acceleration is equal to time because v equals 0. And so then 50 meters per second over 5 meters per second squared gives you 10 seconds for the duration. Pretty easy problem. Just have to know your formulas and apply them. Okay, a ball is dropped from a 100-meter building. What is the final speed and how long did it take to fall? So, this problem, you might say you don't have enough to solve this. You don't know acceleration, you don't know, all you know is initial and height. But you do know acceleration because the acceleration of every freely falling body, so in this case, since there's no force acting on it, it's a freely falling body, there's just gravity acting on it. So the acceleration of any freely falling body is 9.80 meters per second squared. Sometimes you'll see it cut off to just 10, sometimes you'll see 9.81, but usually it's 9.8. So problems like these, you have to know gravity. Acceleration due to gravity is 9.80 meters per second squared. So we'd use v squared equals v naught squared plus 2ax to find the final speed. Plug in everything we knew because there's no initial velocity, so v is just the square root of 2ax. And so then v is equal to the square root of 2 times 9.80 meters per second squared times 100 meters, which is equal to 44.3 meters per second. An important thing to note is if this had asked for what is the final velocity instead of speed, you would have had to say 44.3 meters per second down or negative 44.3 meters per second, even though because that would tell you that the acceleration is downwards. The velocity is downwards, but this just asks for speed, so you just take the magnitude of the velocity. And then how long did it take to fall? So we'd use another kinematics relationship, v equals v naught plus at, v over a equals t, 44.3 meters per second over 9.80 meters per second squared equals 4.52 seconds. So there you go. Pretty simple problem once again, but you'll see a lot of these in kinematics. A ball is thrown at an angle of 45 degrees with an initial speed of 60 meters per second. How long does it take to hit the ground, and what is the displacement of the ball? So this is our first two-dimensional problem that we're working on. This and the previous problem are the most common type of kinematics problem. They're the ones you're going to see the most. You should get used to solving them. You'll even see them later on with like balls launched off tables by springs and stuff. So you're going to need to know how to solve them. Okay, so we would decompose this into vectors, and since gravity is the only force acting on it, then we know that the acceleration is only in the y direction and it's equal to gravity. So it's just little g, it's 9.80. So v naught y is equal to 60 meters per second times the sine of 45 degrees, which is 42.4 meters per second. Since it's hitting the ground, we're going to assume that there's no vertical displacement. It wound up in at the same height as it began. So that gives us everything we need to know to solve for time. And as we said, since time is common across the two dimensions, we can plug that in, and since there's no acceleration in the x direction, we can just take the time of the trip times the velocity in the x direction, and it'll tell us the displacement in the x direction, and the overall displacement since there's no displacement in the y. So let's solve for time. Y equals v naught in the y direction times by time plus 1/2 at squared. So then 42.2 meters per second times by time plus 1/2 times by negative 9.80 meters per second squared times by time squared. That'd be a quadratic, and you can just solve the quadratic. Important note right here, negative 9.80. This, the velocity, the initial velocity and the gravity, they're acting in opposite directions, and you have to differentiate that in physics. You have to say, okay, right, if like east or north, those are my positives, and south and west, those are my negatives. It doesn't matter. You could say south and east are your positives. It doesn't matter which ones you pick as long as that stays constant in every single problem, every single part of the problem you're working on. Because if you start flip-flopping, then you're going to get the wrong answer. You're just not going to be able to remember everything. So you solve this as a quadratic, factor out the time variable, because obviously there's going to be no displacement when time equals 0. And then so you just solve a simple linear equation, and you get time equals 0 seconds or 8.66 seconds. And obviously 0 seconds doesn't make sense as the problem, so it's just 8.66 seconds. And so then you plug that in, so you find the initial velocity in the x direction, which is 60 cosine 45, 42.4, times that by the velocity, and so 42.4 meters per second times by 8.66 seconds, and that gives you that the displacement in the x direction was 367.3 meters. So there you go. How long? It was 8.66 seconds, and the displacement was 367.3 meters. Okay, let's move on to the next problem. A car is traveling at 5 meters per second on the highway when it is passed by another car traveling at 15 meters per second. Enraged, the driver begins to accelerate at a rate of 1 meter per second squared. How long does it take for the driver to catch up, and how far have the two cars traveled? So looking at this problem, you might be saying to yourself, there's not enough to solve it. I only have initial velocity and acceleration. I don't have displacement. I don't have time. I don't have final velocity. But you have two cars. And you know two things, the same two things about both cars. And so that lends itself to creating a system of equations. You're going to see this coming up over and over again in physics. Solve it as a system of equations. Anytime you don't have enough information, you're going to be expected to solve it as a system of equations usually. So, you know the initial velocity and you know acceleration for both cars, because the car that passed the first car, the second car, it isn't accelerating. So you know initial velocity, acceleration, displacement will be common once they catch up, and time obviously will be common. So so x and t are shared, so then x equals v naught times by time plus 1/2 at squared, so 5 meters per second times by time plus 0.5 meters per second squared times by time squared. So, and then x equals 15 meters per second times by time. And so you have two lines right here. This is a line and this is a line. They're both equal to this x. So you can take your calculator and just plug these in and turn the x into a y and turn the time variable into an x, and plug those into your graphing calculator and intersect the two lines. Or you can just solve it as a system of equations, or you can do elimination, or you can use a matrix. There's tons of ways to solve it, but you solve it as a system of equations, and you get x equals 300 meters and time equals 20 seconds. And if you wanted to double check yourself, you could go back, plug that time number in to both equations, and you can see that the displacement is the same. Alright, so let's move on to the next problem. A ball is thrown with an initial speed of 20 meters per second upward from a 50-meter tall building. When does it hit the ground, and how fast is it traveling? So this is a pretty similar problem to what we've already done. It's just now we have an initial velocity in the y direction. So again, we have to remember to set up the negative. I usually use down as negative, but you don't have to. And so it's important to note right here, the negative 50 meters. The ball fell 50 meters. It didn't, so you have to put the negative. So that's why some people would say just negative 20 meters per second because it's one less negative, but that's their choice. So you just have to remember that the gravity and the fall would be in the same direction, so you have to have those have the same sign, and the initial velocity would be in the opposite direction. So we plug in what we know and solve it as a quadratic. Now we have a third variable, so it's easier just to plug this in our calculator and find the zeros. And so the zeros are negative 1.7 seconds and 5.8 seconds. And since you will never ever have a negative time variable, if time only flows one way, so you're never ever going to use the negative answer that you get. It's always the 5.8 seconds. Or, well, it wouldn't always be 5.8, but it'd be the positive one. So v equals v naught plus at, and then you plug in what you know, and that'd give you the final velocity. It's 37.1 meters per second downwards. This doesn't show that, but it'd be downwards. It'd be a negative or downwards. Since it's just asking for how fast, it's asking for speed, so it's just 37.1. But if it had been asking direction, it'd be down. Alright, so problem, oh no, FRQ. Okay, so this one's going to require you to take what you know and combine it and solve this one. So a block starts from rest on a 50-meter long tabletop when a force causes it to accelerate at a rate of 2 meters per second squared. What speed is the block traveling at when it hits the ground if the tabletop is 2 meters off the ground? What is the speed when the block leaves the tabletop? Create a velocity versus time graph for the block and clearly mark when the block leaves the table. Okay, so pause the video, start working through it. I'm going to start working through my solution in 3, 2, 1, 0. Okay, let's begin. So, FRQ part 1. I'm actually going to start with the speed when the block leaves the tabletop, because I'm going to need to know that to calculate the speed when the block's hitting the ground. So, I'm going to start with this, and say that v squared equals v naught squared plus 2ax. So v equals the square root of 2 times by 2 meters per second squared times by 50 meters. So velocity equals 14.1 meters per second. So that gives me the velocity in the x direction. Now it's going to start falling off the tabletop. There's nothing in the y direction, so I can just treat that, the initial velocity, as 0 in the y direction. And so v naught y equals 0 meters per second. And so v squared equals v naught squared plus 2ay, because it's in the y direction. And so I plug in what I know and solve, and I'd say that the velocity equals 6.26 meters per second. Now you might say, well, there's two answers. Which one do I pick? And the answer is you don't pick either one of them. This is your x component and this is your y component. It's asking for the speed. That means both. You have to unify them. So remember how we unified them in the previous lesson. It's the square root, it's Pythagorean theorem. It's the square root, v squared equals bx squared plus vy squared. And so once you unify them, you get that the speed is 15.5 meters per second. If you wanted to, you could find the direction that this problem didn't ask for it, so we can ignore it. Okay, and so now that we know multiple things, we have the velocity, we have the velocity, we have the displacement. We can go to our graph and say, okay, so here's where it's accelerating at 2 meters per second. You can see that. So right here is when it would leave the tabletop. It's just after 7 seconds. And here's the velocity. It's 14.14 and 7.07, I believe. And then this would be the displacement. This dot is when it leaves the tabletop. This is when it hits. Unfortunately, Excel doesn't really like to put 2 lines in one, so this should have a bit steeper of a line, but it connects well, and you can see. And if you wanted to, you could take this right at this point, drop it down, find the area under the curve, and you should get the area under the curve from this 14.14 to this 7.07. That area should be 50 meters. So there you go. And that's all for today. Next week we're going to start covering forces. So that this week we studied the how. Next week we're studying the why of things, of motion. So tune in and have fun this week.